This is Algebra 2 with Trig, 6b.2. We're going to graph logarithmic functions. We're going to do a little reviewing here, and we're going to talk about writing a logarithm in exponential form. So one way to look at this is to go around where the base of your logarithm is the base of the exponential. What a logarithm equals is always the exponent, and then 5 cubed is 125. Number 2, the logarithm does not have a base. It's not written. That implies that it is a 10. This is a common log. If the base is not written for a logarithm, it is automatically a 10. So we would go around. The base is 10 of 5 equals 100,000. So 10 to the 5th power would be 100,000. Now to evaluate, I would suggest to put an equals x. And again, we're going to write this in exponential form. 15 to the x power equals 15. Now you have to use a guess and check type format to help you figure this out. 15 to what power equals 15? Well, we all know 15 to the 1st power equals 15. So x would have to be 1. Here with the last review question, we say the logarithm equals x. We can write it in exponential form, which is 3 to some power is going to equal 1 over 27. Notice how one side is not a fraction and the other side is a fraction. That gives us a hint that there's going to be a negative exponent involved. So to help write this without in fraction form, I'm going to write this with a 27 to the negative 1 power. That's the same thing as 1 over 27, but now I have, on both sides of the equal sign, I have non-fractions. I have 3 to the x, because I can't really write that differently, but I can write 27 as 3 to the 3rd. That's a value of 27. 27 to the negative 1 power. 3 to the x equals 3 to the negative 3rd power. Now that does make sense that the negative makes it into a fraction and 3 to the 3rd makes it into 27. So it's 1 over 27 is 3 to the negative 3rd. So since your bases finally match, and that's what we've been trying to get to, the bases match, x has to be negative 3. So that is our reviewing of logarithms. Now we're going to talk about graphing logarithms. Since we've graphed all the different types of functions up to this point, this is going to be having very much the same idea. The graph of a logarithm that is shown here is where b is greater than 1. And we also have where b is between 1 and 0. Because log base b of x and b to the x, these are those two graphs, because they are inverse functions, the graph is going to be reflected over the line y equals x. We have the line y equals x. We graph in the exponential and we can reflect over to see what the logarithmic graph is. The same idea is happening over here for the exponential decay. The logarithm, when b is a fraction, is going to be a little bit different looking than what it is when b is greater than 1. Note that the y-axis, also known as x equals 0, is a vertical asymptote. That means that the graph is going to be approaching it as it comes closer and closer to the y-axis. It will never reach it. For any of the parent functions, it'll never reach the y-axis. You cannot plug in 0. Your base to no such power is ever going to equal 0. 2 to no power equals 0. So the domain is going to be greater than 0, and the range is going to be all real numbers every time. So to graph, there's somewhat two philosophies. One philosophy is that when we make our table, we're going to pick x values, and that's the 1 over b, 1 and the b, where the b value is your base. And when that's the case, you're always going to get -1, 0, and 1. That's one way to think about it. I'm going to suggest to write your logarithm in exponential form. So if we write the logarithm in exponential form, that would look like 2 to the y power equals x. Remember, a logarithm always equals the exponent. So that's why the y is the exponent. The 2 would be the base, of course. And in exponential form, the x is what the exponential equals. So if we pick values for y, that's going to be easier than us picking values of x and trying to come up with a y that's going to match that. So some very common y values would be -1, 0, and 1. And we can do some calculations with that. 2 to the -1 power gives us a half. So what that means on our graph is that when x is a half, we're down at -1. When y is 0, 2 to the 0 power, anything to the 0 power is always 1. So when x is 1, our y value is 0. Then you can plug in a 1 for y, so 2 to the first power, of course, is 2. So when x is 2, we're up at 1. Now, an advantage for using this exponential format is that we can extend this if we wanted to. We could say, what happens when the y value is 2? 2 squared gives us 4. So when x is 4, we're up at 2. And when y is 3, x is 8. So if you extend it, sometimes that's appropriate. We can see that the logarithmic graph continues to grow as x gets bigger. Notice that the graph is never going to touch the y-axis unless there's a translation. So we have an asymptote here at x equals 0. And you want to label that on your graph. So our asymptote is x equals 0. We connect the points to make a curve. We notice our domain. Think about what your domain is. What are the x values we can get? Look at your graph. Look at your table. I don't have any negative numbers in my table. Even when I use negative numbers for y, I'm not getting negative numbers for my table. And as I look at it, it's approaching but never touching the y-axis. That means my x values can only be greater than 0. My range, my y values, can be any number. It clearly goes down and slowly but surely goes up, so it's all real numbers. There is no transformation in the comparison. There is no reflection, no stretch, no translation. For our graphs, in this class, we will only do translations with logarithms. And then end behavior. As x approaches, we typically talk about when x approaches negative infinity, when it moves to the left. How far to the left can we go?
0.
Right, we can't go to the negative numbers. We can't actually ever touch the y-axis. So as x approaches 0, the y value is heading downwards, is going to negative infinity. The closer we are to 0, the further down the y value goes. As x moves to the right, notice that there's no limitation to what the y can be. So that would, or the x would be infinity to the right. And the graph would slowly start to climb. So we have our graph of log base 2 of x. All right, on the flip side, we have worked with h and k with most all of our functions. And we know that we're first going to graph out the parent function, which in this case is going to be y equals log base b of x. And then we're going to translate it. Horizontally, h units, and vertically, k units. We've written that for most every type of function we've done so far. The horizontal asymptote will always be where the h value is. It's a vertical asymptote for a logarithm. So if the graph translates to the right, it's going to be x equals a positive x number. If it translates to the left, it'll cross the y-axis, and it'll go all the way to the negative h. So here we are with the logarithm base 3 of x minus 1 plus 2. This has a translation. We're going to sketch our graph first of y equals log base 3 of x. We're going to do the parent function first. So we're going to have two graphs on our paper. We're going to write this in exponential form. So 3 to the y power equals x. Now we can pick our values that we want to plug in. When 3 is to the negative 1 power, we get 1/3. When 3 is to the 0 power, we of course get 1. Any number to the 0 power is 1. And 3 to the first power is always that value. So we can graph this out. When x is 1/3, we're down at negative 1. When x is 1, we're at 0. And when x is 3, we're up at 1. Now we can continue this. We can put a 2 in for y, and we can square the 3. That would be out at 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that would be up at 2. So that gives you an idea of how to draw in your logarithm. Now, when you're graphing this out, if you were to use a calculator is going to give you the impression that it stops. You would have to keep zooming in to watch the line keep going down. So it'll be very clear if we're using a calculator, because people have their graphs drawn incorrectly. You need to draw it going down forever. Now we're going to translate this graph, h and k. We know our h value is 1 and our k value is 2. So we're going to translate right 1 and up 2 units. So we're going to go to the right 1 and up 2, to the right 1 and up 2, to the right 1 and up 2, and even here we're going to go to the right 1 and up 2. So it's good if you trace that out with a different color. Highlighter works real well, doesn't bleed through the paper as much. So we have x equals h, which is x equals 1 for our vertical asymptote. We know our domain is greater than h. The range is all real numbers. We had a translation right 1 and up 2. And for end behavior, as x approaches, what's the smallest value x can approach? It can get and approach 1. So the y value at that location, the closer you get to 1, the more down it goes. So it goes to negative infinity. And it goes to positive infinity to the right, and the graph slowly but surely increases to positive infinity also. If the asymptote is x equals 1, we would know that the domain is x equals 1. Looking at the pink graph, when we fill out our domains and range and all of this, it's for the final graph. So that should be a 1. These two graphs here at the bottom, they're a little bit different because the base is between 0 and 1. We're going to set it up in the same fashion where we say 1/3 to the y power equals x. We're still going to pick negative 1, 0, and 1. So 1/3 to the negative 1 power is the reciprocal of that. 1/3 to the 0 power, and 1/3 to the first power. So we know how to plot our points. 3 to the right, and 1 down. 1 to the right, and 0, 1/3, and 1. So notice that when the b value is less than 1, but greater than 0 still, it's going to curve in a different direction. The asymptote is still the y-axis, which is x equals 0, and your graph is log base 1/3 of x. So since these are u-try, you go ahead, pause the video, work through this, graph the parent function, then do the translation. You should have 2 graphs for your answer. All right. I stated the domain and range and the end behavior. There were no transformations happening to our parent function. Over here, our parent function is going to be log 1/3 of x. And we're going to turn that into exponential form and use y values of -1, 0, and 1, which is going to be 3. When you take 1/3 to a negative power, you flip the fraction. 0, any number to the 0 power is 1. And the first power always makes it that b value. So when you're out at 3, you're down at -1, 1, 0, and 1/3, 1. So you can clearly see that this is a decay, and we're not surprised because the b value is between 0 and 1. So this is a graph, log base 1/3 of x. And we're going to translate that graph. Translate 2 units left because h is -2. And 3 units down. So 1, 2, 1, 2, 3. 1, 2, 1, 2, 3, and 1, 2, 1, 2, 3. So we know that this is going to follow along our asymptote curve and forever keep dropping. And that graph is going to be y equals log base 1/2 of x plus 2 minus 3. The domain is going to be from your asymptote, which is x equals your h value, which is -2. So x is greater than -2. And the range is always all real numbers. And the end behavior, we can only approach the asymptote, so we're approaching -2. The graph in this case is going upwards to positive infinity. And as we move to the right, the graph is slowly but surely going down. So apparently I was using the same type of problem we had up here as 1/3. These are 1/2. And I had it all twisted all over the place in here, huh? So this should really be 1/2, which would make some minor changes. It might just be easier to change the original equation. That would change this to a 2. That would change this to a 1/2. We'd have a little minor changes over here, but for the most part, the domain and the range and the end behavior don't change.